All right, well, I guess I'll get started and see if any other people join in. I have been, sorry about that. I have been asked by NASA EPSCoR program, YEPI Compton, I believe, to summarize two things. Summarize work we've done for NASA through the EPSCoR program. The state of Iowa has been on and off again EPSCoR eligible, and they've changed the rules a little bit lately so you can stay EPSCoR eligible a little bit longer. But before, in my first EPSCoR grant, the top grant you see there, just about as soon as we got EPSCoR eligible, we became un-EPSCoR eligible. So it's been on and off again, but I've had two grants, and I'd like to do today is summarize a little bit of the work that we've done on those grants. But then the second half of the talk, Yeppe asked me to talk about all of the success that I've had in using the NASA grant kind of as a springboard to achieve other funding, achieve other work in this broad area. So I'm going to summarize the work that the follow-on work that led after this first grant, the NASA EPSCoR grant, and also the second NASA EPSCoR grant. So if you have any questions or anything, I think the audience is pretty small, so please jump in maybe with chats. I don't know if your audio is enabled, but probably chat is, and I think I could probably find that. So anyway. I'm Steve Martin from Material Science and Engineering at Iowa State University. Been here a long time and have been funded by a variety of sources. What I show over here, you can see my cursor, are the NASA sources of funding. I'll show a more detailed list at the end. The laboratories through NASA that I've been working with primarily are the JPL laboratory, Pasadena, California, of course, and the Glenn Research Center in Cleveland. So let's get started. What are we working on? So, oops, got to use, mouse doesn't work for these. There we go. So the work that I've been doing and conducting for NASA, of course, is very basic research. We don't build batteries that NASA can use. Our work is directed towards next generation batteries that will enable missions, primarily working with JPL and Glenn. Our types of batteries, as I understand them, are going to be more used for rover type vehicles like that is on Mars right now. And of course, in those applications, you're always interested in increasing the energy density. The lithium-ion batteries that all of us depend upon every day in our cell phones, even automobiles, are the graphite transition metal oxide batteries. And graphite stores the lithium relatively safely on the anode. And the transition metal then, of course, is the redox couple. And you get, depending upon which particular transition metal you use, most of us now have shifted over to the nickel manganese cobalt system to reduce the amount of cobalt. When they were first invented 30 years ago, lithium-ion batteries were pure cobalt, and that's way up here around 4 volts. We suffer a little bit lower voltage by going to the manganese nickel couple, but you reduce the cost dramatically by getting the cobalt out. But anyway, the long story short is that the capacity in units of which we, in the battery world, and I don't know how familiar you folks are with batteries, but in the battery world, we use something like milliamp hours. So 1 milliamp hour means that you could draw 1 milliamp of current from your battery for an hour. And then, of course, because batteries are all portable batteries are very dependent upon their mass, we then take that and divide that per gram of battery. And so the traditional lithium-ion battery that we all use every day is in this 300 to 400, maybe 500 milliamp hour per gram basis. And it's low because we think about that number as being low, although lithium-ion is much more energy dense than lead. It's low because it has to be, the lithium is stored in graphite. It takes 6 graphite atoms to store 1 lithium ion, so low density there. And of course, all these transition metal ions, you can see here 2 minus Y and Y. Even if X was 0, you'd have 1 lithium stored in 2 plus 4 atoms, that may be another 6. So that's 1 to 6. And so it's just low density because they're just not lithium rich. Well, if you move out this axis a little bit to sulfur and react with sulfur, it turns out that lithium, 2 lithiums react with 1 sulfur. And so instead of being 1 to 6, the energy density goes from 2 to 1. What is that? A factor of 12. So you go from the 300 or 400 down here to the 2000 or so with the lithium sulfur. Ultimately, you'll see batteries that we call air breathing batteries. Sulfur is pretty heavy, 32. Oxygen is pretty light, 16. If you had an air breathing battery that used oxygen as the cathode, then you could go lithium 2, oxygen 1, and then not have to carry around the cathode. You just breathe the air just like an internal combustion engine does. And those will be coming in 10 or 20 years. But the intermediate step, which everybody is working on, NASA included, is lithium sulfur. Air has a problem for NASA because there's not very much air around in places that they tend to visit. So they use the advantage of sulfur. So our work is on developing new lithium sulfur batteries for NASA. Our particular approach is a solid state approach, where we can increase the energy density about a factor of 10, like you saw, from a 300 out to a 2000 or so. But we get rid of the flammable liquid electrolytes. And another big aspect in terms of reducing volume and reducing weight is the ability to form these solid cells. And so the Teslas, for example, that Elon Musk makes, they're all based on about 70,000 or so what are called 18650 cells, 18 millimeters in diameter, 65 millimeter tall cylinders. And when you stack cylinders, of course, you lose all this space. Well, Tesla and others utilize that space because they have to cool the batteries, they have to heat the batteries, they have to monitor temperatures and so forth, because the liquid electrolyte is very temperature sensitive. If you got rid of that and moved to a solid state structure, then of course, 2 things: they pack much more efficiently. You don't lose all that volume, but because they're solids, they're not going to be like concrete, but they're going to be on the order of the types of ceramics that concrete is, so silicates and aluminates and so forth. So you just don't have to worry about them getting too hot. In fact, they run better when they're warmer. So you don't have to have all that extra temperature control, and that's exactly what is advantageous for NASA, especially as they envision missions to Venus, where the surface temperature is very hot. So we envision using solid state approaches that have wider temperature ranges, up to about the melting point of lithium, which is about 200 degrees Celsius. But they also can operate at low temperature. All of the diffusion is, of course, controlled by the Arrhenius expression. You get too cold, and the ions eventually do slow down, but they don't have the freezing out problem like liquid organic electrolytes do. When you run lithium batteries too high, you've seen the hoverboard or whatever they're called, fires and car fires and so forth. A pretty common source of that fire is when the lithium doesn't get tucked in and safely intercalated by the graphite, and it stays out on the edge. Here's a little cartoon by Mark Duff. And what happens is the lithium ion, instead of getting tucked inside and intercalated into the graphite, it precipitates on the outside, forms these little wires, these little dendrites, and here's an actual SEM of a dendrite. And they grow across the battery and short the electrolyte out. The distance is only about 30 microns. I'll show why that's important to have that short distance. Diffusion, it's a root diffusion problem. But it doesn't take much of a dendrite to short out the battery. You short out the battery, it's just like shorting the terminals. You get heat, you get fire, and then eventually you cause bad things like this. Now, this vehicle is not a battery-powered vehicle. It was actually caught on fire by a cell phone that caught on fire inside the vehicle. So the solid state systems tend to be a lot more abuse tolerant. So what are we trying to do? We're trying to develop these all solid state lithium batteries, not only make them more energy dense, make them lower cost, and make them higher performance. And my story and my work and my area is all about the separator between the anode and the cathode. Where all the ions have to move from the anode to the cathode during discharge. They move from the cathode to the anode during charging. And the reason we work with glasses is because with glass, they're a frozen liquid, and you can take advantage of the wide solubility range in the liquid state, and then you freeze that to the glass. And then because you can change the composition over wide ranges, you control properties, and as a result of that, you can adapt the glass to meet all of the many properties you need for a lithium battery. I'll talk about those requirements in a moment. But we all know that glass is a low-cost material. I'm looking out my beautiful window in my office. Mechanical engineering is across the way there, and glass is a known commodity. It's pennies per pound, honestly. And so the cost, which may not be an issue for NASA on most of its missions, however, for portable electronics, automobiles, it is a major issue. So we can get rid of many of the costly components of a battery by using these low-cost glasses. I won't go into the details of it, but glasses don't have grain boundaries. They're homogeneous frozen liquids in there, so they're continuous. There's a detail about how the dendrites grow in the material, and one model has them growing along the grain boundaries in a polycrystalline ceramics. We don't have those, so our materials are more dendrite resistant than other types of materials. What that does for you, they're more favorable towards high critical current densities. A critical current density is that current of lithium ions, not electrons. Remember, the electrons are going in the exterior circuit through the car or the cell phone. It's the lithium ion current through the battery. You want that to be as high as possible because every lithium ion has to be matched by an electron. So the high conductivity, the high current allows high power from these batteries, and these grain boundary free glasses promote higher critical current densities before they fail. So it's another technical advantage of the glasses. In the interest of time, I won't go into all that, but suffice it to say, our project then is to replace these carbonaceous cobalt lithium ion batteries where the separator is a piece of plastic filled with liquid. And here you can see the cartoon showing how many carbon atoms it takes to store one lithium ion. So that's why they have low energy density. It just takes so much carbon, 6 to 1. Cobalt's a little better, 3 to 1, but you can't take all the cobalt out. X is about 0.5. So it's 0.5 to 3 or 1 to 6. So from a battery engineer perspective, that's not bad. 1 to 6 over here, 1 to 6 over here. The amount of material is about the same, so it makes it easy to manufacture. But that dilution of lithium really lowers your energy density. And our structure will look like this: lithium metal with a very thin separator and lithium sulfide. Our reaction is 2 lithium to release 2 electrons. That goes in the external circuit. Those 2 electrons then reduce the sulfur to form lithium sulfide. And then, of course, when you are done with the battery and it's all the lithium sulfide has been formed, you just hook it up to a power plant, your AC circuit at home, and you drive this reaction backwards, separate the lithium from the lithium sulfide, produce lithium and produce sulfur, and you start all over and you drive to the grocery store or the next rover location on Mars as is needed. So I won't tell you too much about the work we're doing in the interest of time, but I just want to show you a little bit of the work that we do, and then I'll go on to the details of what has happened as a result of our funding. We have all kinds of targets. Sometimes they're involved with cost. Lithium ion conductivity is really important because the faster the lithium ions move, the more current we can draw from the battery, and the faster our automobile can travel. There has to be a very low electronic conductivity, because if you have electronic conductivity through the electrolyte, remember, then that'll short circuit the battery, or more likely, it just drains the battery. The shelf life of the battery decreases with time. And we also want to make them as easily as possible to manufacture, and we want to reduce the cost as much as possible. And of course, on other benefits, we want them not to be toxic and low reactivity and chemically stable and so forth. So they're just easier to manufacture. So this is all that we do in our group. I'll only talk about the top one just in the interest of time. We make thin film glasses. We developed a lithium sulfide composite. We make the anode with lithium metal based. and then we build and test the batteries. I won't go into all 4 of those because I think that's beyond the spirit of what I was asked to do, but I do want to tell you a little bit about what we do. And so I'll focus on just one fourth of the story, as it were, these new thin film glasses that we make. And I'm going to tell you a story about 3 different compositions: a pure sulfide material, an oxysulfide material, and then our newest and best material, an oxysulfide nitride material. Remember back to the original story, I said that the glasses can dissolve many components. Well, now you can vary the composition. The sulfide glasses were among the first to show high conductivity, but the sulfide, pure sulfur, is actually reactive. We can add the oxygen to oxidize the glass and stabilize it a little bit. We can add nitrogen to even stabilize the glass even further. And again, it's just this compositional optimization. The compositions are kind of complicated, but if you think of lithium sulfide as sodium chloride, and you think of these things out here as water, it's really just sodium chloride dissolved in water, except now the phosphorus sulfide and silicon sulfide, that's more of a liquid that we quench to a glass. But it turns the otherwise insulating phosphorus sulfide and silicon sulfide, like H2O, except for the ionization, a little bit of ionization, it turns the otherwise insulating network structure of the glass into a lithium ion conductor. We're interested in glasses, so we quench them to glasses. We have this thing called a glass transition temperature. We warm it up, and then it crystallizes above TG. This is our working range. It's where down here the glass is brittle, we can't really work with it. But here it's a viscoelastic liquid, then it crystallizes. Think taffy and sucrose sugars and so forth. You know, you get a taffy, you get a liquid viscosity. Well, those also crystallize. Well, as we add oxygen, we push that out a little bit more. And as we add nitrogen, we push it out even further, about 100 degrees. And that gives us a range of temperature where the liquid, the glass, is viscoelastic. We can stretch it, we can pull it into thin films. We can form it into thin films, just like the polymer people do in extruding their thin films. And the thin film is important because we want to have fast ion conduction across the battery with very little resistance. I'll show that in a moment. And this just shows a picture of the surface of a glass, and here's a typical sample. But anyway, the silicon phosphorus oxynitride is a glass that we optimize because glass is this, like we say, this universal solvent. And we add nitrogen because it's a very strongly bonded anion and strengthens up the network and reduces the resistance, improves the resistance to crystallization. One of the first things we do is something called cyclic voltammetry. And cyclic voltammetry kind of imitates a battery. Down at 0 volts, that's where your battery starts. When it's charged at 4 volts, that's where the battery is limit of the voltage on the cathode side. And what you see here is there's some current, there's some stuff going on, there's some oxidation, there's some reduction of the glass. I'm sorry, that's a typo. That's supposed to be the LPS, and this is supposed to be the LPSO. The color is right, but the scale, the names are wrong. But as we add some oxygen, again, I apologize, that's supposed to be over here. We narrow that current. There should be no current. There should be no current, electron current through the anode, so it's getting narrower. And then when we go to the oxysulfide nitride, this is microamps, so this is 20 nanoamps. That's very low current. You can see there's almost no electrochemical activity. It's just basically a straight line, showing that in fact the glasses are very insulating to electrons, but very highly conducting to electrons. And so the oxygen and nitrogen suppress these side reactions, because of course we don't want the battery to sit there and react. We want it to be perfectly stable, and we only want it to react, as it were, when we draw battery. So we get 4 volts. Why is 4 volts important? Well, that's the voltage that you operate, cobalt oxide, nickel manganese cobalt oxide. That's the voltage of the lithium ion battery. So we need to be able to be stable out to that 4 volts, and you can see these glasses do that very well. We do other thing called electrochemical impedance spectroscopy. That's where we it's kind of a really strong test of the chemical stability of the battery. Of the electrolyte. we take a glassy electrolyte here, a tablet of the glass, and we sandwich it between two pieces of lithium metal. Lithium metal, of course, is really reactive, which is why we use it as a battery material. And what we don't want to happen, here my label is correct, what we don't want to happen is shown here. The glass immediately reacts with the lithium and forms impedance. You can see this is impedance. You can just think of the glass just reacting with lithium and forming an interfacial layer. It's like oxygen forming alumina on aluminum. It's like oxygen forming iron oxide rust on iron metal. And that barrier, of course, increases the resistance dramatically with time. I show that here. You start off with a couple hundred ohms and you end up only after 24 hours with what's that, 30,000 or so ohms, very high impedance, makes the glass battery completely unusable. When we add oxygen to the glass, we stabilize it dramatically. There's a little width here, but the impedance is 4,000, but we still get some interfacial. It's hard to explain all the complex impedance diagram, but this is due to the bulk of the material. And a perfect response would be just one single line. It wouldn't change with time. Here it's changing dramatically. We know that's reacting. Here it's changing a little bit, so the oxygen helps a lot. And then when we go to the oxysulfide nitride, notice the scale is the same, 5,000. Let me go backwards. Notice that scale is 5,000. Look how small the arc is. Well, the arc is small because the conductivity is so much higher and it doesn't change at all with time. So this is showing us that the oxysulfide nitride chemistry is very stable to lithium. What's that mean? You could put your battery together, let it sit there for 5 or 10 years and it would be stable and your battery would work when you needed it to. So showing that the glass is stable to lithium metal means we can use the glass as a solid electrolyte in a lithium metal battery. Just to show you that we can cycle these things a long time. This is hundreds of hours, of course, in real use it'd be thousands of hours, but for NASA, hundreds of hours of missions is okay because this is hundreds of hours, but many tens, almost 1,000 cycles. And so that's typical. A couple years of cycle life is really all we need. Automobiles, right? You would cycle them every day and you would use them for 10 years. That would be 4,000 cycles. This wouldn't work for them yet, but they work well for the types of applications that, that NASA needs. This just shows that we can cycle the battery back and forth, back and forth, back and forth. But eventually when we push it too hard, here we've abused the battery because we want to see where it would fail. It fails out here about 2 milliamps per square centimeter. Your cell phone operates at about 1 milliamp at maximum. Cars operate at about 3 milliamps of current, ionic current per square centimeter of electrolyte. So we're getting very close to even automobile level types of performance. But so far, we've been talking about these very thick pieces of glass, and I've been mentioning that these very thin films are necessary. And why are they necessary? Well, let's start off with our 4 volts we get out of the cobalt chemistry. And let's look at the overpotential inside the battery. Remember, whenever you have a current through a resistor, it always gives you an ohmic resistance, right? V is equal to IR. In this case, it's not the electrons in the exterior circuits, it's the ions through the middle, through the solid electrolyte. So it's the ionic current through the glassy solid electrolyte multiplied by the resistance of the glassy solid electrolyte. But Ohm's law still holds. So let's choose 1 milliamp as a typical type of kind of mid-range current, a little lower in some applications, a little higher in some applications. We'll choose 1 milliamp. And this is the conductivity. And this is the resistance goes up as the thickness and down as the area. And I've chose 1 square centimeter as the area. Now we want a very small overpotential. About 1%, right? We don't, if we have any larger than that, say, 4 volts, if we had 4 volts of overpotential, that 4 volts would counter the 4 volts we'd apply and we get 0 volts out of the cell. So in this case, you would get 4 volts chemistry minus the 0.01 volts to be 3.99 volts. or in our case, 4 volts would be 1% would be 0.04 volts. And we have our current, 1 milliamp. We have our conductivity of these things, about 10 to the minus 3, 0.001. And you can do the simple math, and you would, in order to get such a small overpotential, you get about 40 microns. And so that's why we need very thin films. And that's where our glass comes in, where we can pull the glass into a very thin film. We can stretch it just like tappet. Just to do a simple calculation, you've heard a lot perhaps about the gigafactory that Tesla makes. What is a gigafactory? Well, a gigafactory is a gigawatt of batteries. So what does it take for thin films to get a gigawatt of energy? Well, if you take a 2,000 gram, a 2 kilogram preform, that gives you about 1,000 cubic centimeters, about 2 grams per cc. You pull it about 20 microns thick, a little bit thinner than the 40. That gives you about 50 square meters of thin film. You've got 4 volts, and you have used 10 microns of lithium, the chemistry and charge. You get about 30 megajoules of energy out of every one preform. Well, 30 megajoules dividing into 1 gigawatt makes about 34 preforms. So you could make a gigawatt every day by having 34 draw towers pulling 50 square meters of glass every day. Glasses are relatively cheap. They're in this 25 cent per gram basis. And so you can get into the $10 per square meter using these types of chemistry. Seems like a lot, but that's actually cheaper than cotton fabric you buy at the quilt store. So let's talk about, let me wrap up then, talk about thin films. The way we make thin films is 2 steps. We melt a whole bunch of glass, we get it nice and uniform, and we pull it. You can't see it here, I'll show you a video in a moment. You pour it in and you cast it into a pre-film. And then we just take that glass preform and draw it. This works, yes, well, it's working. This is a student of mine, Adriana. And she's lowered the furnace out, and you can see she's got a crucible full of glass, and she's swirling it around to make it uniform, and she's pouring that onto a hot plate. And that hot plate is just warming the glass up so all the glass comes to the same temperature, right below the actual softening point. We're going to heat it up higher than that, but to quench the glass, we need a bit lower than that. So she's gonna, then you can see the furnace raising back up again. And so this top plate's been heated to the same temperature as the bottom plate. And there you go. And we get a nice preform then. Let's go backwards. My slide, if I could do that. Yeah, we get a preform that looks like that. We take that preform, take that preform, take that preform, and we load it into a furnace inside a glove box because dust and particles, and we simply draw it out like taffy. Now it's really hard to see because glass is 20 microns is pretty transparent. But if you look real carefully, that's one edge of the film, and that's another edge of the film, and then the glass is between that. We just pull it out, and we get rolls and rolls of thin film, about 20 microns thick. We get about 10 centimeters wide. We get these 10 meter plus preforms. We don't make the kilogram preforms yet. That's just a lot of glass. We don't need that much glass. We use about 250 grams or so. And here's just a micrometer. We break off a little piece of that. We're pulling about 19 microns to 20 microns, so we can pull that. Just one more detail, and then I'll move on to other aspects. When we pull the glass, we have to know what temperature to pull it at. We have to know what viscosity to pull it at. So we do, the students do a lot of work in measuring the viscosity. You know that when you have a material that's cold, it's stiff and hard. When it's hot, it's low, it flows. And that's all this is saying. This is just temperature. And we can look at the film drawing range in here. But one of the things we have to worry about is crystallization. Remember, a glass is a supercooled liquid. It can crystallize. And so we have to worry about crystallization. We don't want crystallization up here in the film forming region or crystallized during pulling. We want that crystallization temperature to be up here so we never get it hot enough that it would crystallize. So we do experiments to determine this temperature dependence. This is experimental data. This is experimental data. And the blue fit is our experiment to fit. It's a kind of complicated model to get it accurate enough, but we can do experiments to determine the parameters, and we can predict the viscosity very nicely because the viscosity is not real well known in this region that we need it. So we can predict what temperature to draw our film at. But we also want to study the crystallization. Where does the glass crystallize? So we do a series of what are called differential scanning calorimetry. We just measure the heat capacity. We see a nice change at the glass transition temperature here, and then we see crystallization events. We do that as a series of heating rates, and then we do a simple Arrhenius plot. I apologize for going into all the details here, but we simply extrapolate this out to where our draw conditions are. About 1 degree per minute. We heat it very slowly, and that gives us our draw temperature. Gives us our crystallization rate at our draw temperature, so we know where we're at. And then we can plot that here, our 400 degrees. And we say, yep, our draw temperature is at a lower temperature than our crystallization temperatures. Therefore, we can draw without the glasses crystallizing, because if they crystallize, of course, then we can't draw them into thin film. Again, just to show you. So let me wrap up this part. The glasses are fun to work with because we can draw them, we can work with them, we can change the composition to be high conductivity, low crystallization resistance, chemical stability. And we can do all these things through continuous variation of composition. There are crystalline conductors, but the problem is with crystalline conductors, you're kind of forced into the phase diagram. You can't dissolve things as well as you can in the glasses. So let me go to the next part of my talk and talk a little bit about the things that have happened. I'll break it up into 2 parts. My first grant was like 2013 to 2019 to current with present. And so I'll give it in 2 sections, go by each year through the grant. The first is we just use the grant to help us be springboard to develop collaboration. We had collaborations with the Jet Propulsion Laboratory. We developed some DARPA proposals because kind of not quite, but kind of a name association when we were kind of approved by NASA to do funded research with them. That kind of opened up doors for us that, oh, you're funded by NASA, so therefore maybe we could write proposals. So we did lots of work with that in various laboratories, the JPL, of course, Glenn Research Center, but also Oak Ridge National Laboratory, big battery research center. And we use this local, another very important aspect, this research funding supports the support services. I don't know how to say that. It supports mechanical shops, the glass blowing shops, the electrical shops. That helps to strengthen our overall research enterprise because of course we break things and we need those repaired. We make glass apparatus. So we need the glass blowing studio and glass blowing shops, I'm sorry. And that helps us in our research. And then, of course, people are quite interested in the NASA research that we do. NASA just has a lot of name recognition. And when you're NASA supported, people want to hear from you. So that gave me an opportunity to give various talks on campus about our battery research that we're doing in conjunction with NASA. And of course, through this funded research, we hire postgraduate postdocs and undergraduate researchers and graduate students and so forth. Parallel to that, Iowa State has, of course, been very active in building research capacity. We've hired a number of faculties across the university and our part of the College of Engineering. And even then in our department, we brought in 2 new faculty over that period of time. We hired new laboratory support staff and then informational IT. Of course, these folks were not supported by the NASA grant, but I'm just trying to give an impression of the synergism between the NASA grant and things that are going on at Iowa State. And then a big part that helped us was a large $2 million effort and the College of Engineering to build and help and buy and acquire laboratory instrumentation and renovate laboratories. And our laboratory here at Iowa State for this program benefited from that. Then Iowa State did build another research building and also increased funding for our ISU research project. There's a lot of spin-off technologies, of course, that come out of our battery research, and we've been involved with the ISU Research Park and part of those. And then parallel to all of that, of course, is the research funding. This was the grant that we had. It was $750,000 with a 50% cost share over this period of time. And then it helped us springboard to National Science Foundation work for our fundamental research through funded by the National Science Foundation, but also instrumentation and AGEP fellowships, this minority underrepresented persons support that allows us to add additional persons, graduate students to our group. So that's about $1.8 million of additional research or funding research that we had in 2013. Again, in 2014, we started another separate project with JPL to do a very specific focus research project. I traveled internationally to describe our research. We had some students from Osaka National Laboratory, Osaka Prefecture University come to Iowa State. We collaborated. I'm a big proponent of supporting underrepresented persons in STEM fields. So I collaborated with Prairie View A&M and Tuskegee University. They're very interested in our NASA funding. So it kind of opened up some doors. Also collaborated with South Korea. South Korea is a major battery research and development country, of course. LG Chem and so forth make a lot of batteries, and so we're collaborating with them. I spent a little bit of time at Glenn Research Center to continue and expand our research. Continuing our funding, the College of Engineering did a $20 million renovation of our Marston Hall, which was our very first engineering building, and that was renovated and turned into a general purpose classrooms and lots of administrative spaces, and they have continued support for the ISU Research Park. For me personally, this grant helped do continuing our battery research. I worked with my former major professor. Again, it's kind of name recognition. Once we got supported by NASA, then other things seemed to happen. We got a grant from the Department of Energy and their Office of Energy Storage to do a sodium battery, very different battery than lithium, but sodium battery for grid scale energy storage. And that was a lot of fun to work with. Also, then DARPA got involved, and so I got a subcontract from Charles Draper Laboratories, and also then we got some more additional funding from the Chemical Engineering Program, National Science Foundation, for about $300,000, and then we also got a travel grant to talk to folks in Germany and South Korea. Continuing on, again, we had a small project with NASA, and then we did a project with small nuclear reactors, somewhat unrelated to the battery work, but very related to the kind of the sulfide chemistry. And again, this continuation funding from DARPA. So in 2004, it's about 1.6 million. Honda got involved in our research, got very aware of our research that we were funded by NASA. And so we had the start of about $170,000 per year. Ended up that grant was terminated after 1 year. Honda corporate decided to move all their battery research back to Japan. And so that unfortunately ended a bit early. And then a big grant from ARPA-E for about $3 million to develop some sodium batteries for grid scale energy storage. We bought some more equipment to help characterize using NMR spectroscopy. We hired 2 new faculty members in 2015. Again, started collaborating with PolyPlus, a battery company out in the Bay Area. And so all of that funding correspond to about $3 million, a big year, 2015, about $3 million of funding in 2015. Continuing, was really fortunate in 2016. We hired a Professor Shu that was a battery person, and we started a new laboratory. And then we got our second ARPA-E grant now for solid state lithium batteries. So I was running 2 ARPA-E grants at the same time. We got a new X-ray diffractometer, we got a new SCM, and then I had remember my STEM work, we had a Gary DeBoer, professor from LeTourneau University in Texas, and he came up and did some work with us. And we also hired through our STEM work, California State University, we hired underrepresented PhD graduate student. Lots of funding. We had the EPSCoR grant continuing. We had the ARPA-E grants continuing, and we have some grants from Honda as we phased out that project. As I mentioned, it ended after 2 years. They did give us a little bit of grace money to end it relatively easily, and we got more supplemental money to support underrepresented persons in our STEM field. So 2016 was about $3 million. So over the period of time that we had that grant, including got about $10 million in research funding. Of course, that was in part due to my effort, but I will say a lot of it was it was kind of a tipping point. Once we got funded by NASA, it was kind of a gold standard that said, "Whoa, maybe Professor Martin knows what he's doing." And as a result of that, it just seemed that the grants kind of opened up a little bit more than in the past. Well, unfortunately, we became uneligible. Iowa State got too much money, I guess, due to the old rules, and we became uneligible for fiscal year 17 and 18. But we became eligible again in 2019. So we got now another DOE grant for about 1.4 million over 3 years, a new NSF grant, and also another $500,000 grant, actually from the state of Iowa, to support grid scale energy storage. And we built a new building at Iowa State for about $84 million. As most of you probably also experienced, 2020 was just kind of holdover year. Not a lot of activity that year due because of COVID. We all went home and worked from home for a year, so there wasn't a lot of work going on. But in 2021, things kind of started back up again. We were able to get another NSF grant to acquire an instrument. We got another supplement for our supporting our minority underrepresented person in STEM. And then we also got some grants from Iowa State to help us buy some instruments. As I'm indicated, Iowa State have been strongly supporting instrumentation. And then again, another grant from the NSF. So far, the monies aren't quite as large as they were in the first grant period, mostly in part due to COVID, because we pretty much lost that whole year. But nonetheless, about $3 million over the period of time that we've been funded by my second NSF EPSCoR grant. And so over the periods of time that we've been funded by NASA EPSCoR, we've brought in about $12 million, almost $13 million in research funding. So again, it's been a very important tool for not only supporting our research, but helping us build additional connections to additional programs. So of course, when the NASA EPSCoR programs, when they sunset, of course, then I've made these connections to other agencies. All their programs are 2 or 3, 4 years as well. But by having that connection to the other agencies, it's really helped us develop continuing funding in this really critical battery research area. Just again, things that we've worked on, we've continuing our collaboration with Jet Propulsion Laboratory. We've continued our work with work with General Motors. We're bringing in new people. We had Latorno University in Texas. Now we're collaborating with Minnesota State. It's a little closer and a little easier for that faculty member to get back and forth between Iowa and Minnesota. But let me finish up. I apologize if I went too long. I think I talked for about 40 minutes. Sorry about that. But just to give you an idea, I've been funded by NSF continuously. So I've had funding at a kind of a base level. And then when the NASA program came in, all these other agencies, ARPA-E with those 2 great big grants, Energy Efficiency and Renewable Energy Vehicular Technology Office was really helpful in really redoubling our support. But also even the state of Iowa is now funding our work, as you've seen here. But of course, all this work is done not by me. I'm just the group leader. This is the current cohort of my research group. This is the 2022 cohort. I have typically 15 to 20 students in my group. I think there's 12 or 13 students there. A mixture of graduate students and postdocs and undergraduates. Currently, I have just graduate students and undergraduates. And with that, I'll close and apologize for taking the time, but hope it was helpful, learning a little bit about how we at Iowa State have used the NASA EPSCoR funding to really redouble our research in battery research and development. So thanks for your time. Yeah, Kevin.
Hello, Dr. Martin. Thank you very much for joining us. I had some follow-up questions. I just wanted to give some time in case other members of the audience wanted to raise their hand.
Sure.
All right, so it looks like I'll kick off some of the questions. You
Sure.
had mentioned that the NASA funding really felt like it opened a lot of doors for you
Yeah.
in building connections to other agencies and other funding opportunities. I'm very curious about whether you feel like that was due to some groundwork that had happened beforehand, or this was something that once you got this particular EPSCoR award in hand, you were able to go forward and be a bit more aggressive in advertising. How would you describe that experience?
Yeah, it's a great question. I don't know the answer to it because, it's a one sample population. So, but I think it's probably fair, a synergism between both. Of course, as faculty members, we're constantly striving for funding and writing proposals and so forth. But it just seemed that when that NASA EPSCoR grant came in, which was the first, it just seemed, to use the old analogy, the floodgates were open. And it just seemed that all of this happened because prior to that, I was running about one NSF grant, maybe an NSF grant and an NSF instrumentation grant, maybe one single Department of Energy grant and so forth. So it's just truly my experience that once I got the NASA EPSCoR grant, it just seemed like everything came together. Now, to be fair, also, the United States as a country has decided, it seems, that battery research is now important and battery research needs to be funded. And that wasn't always the case. I've been working in batteries all my 40 years at Iowa State. But I just couldn't use the word battery in my proposal because battery research just wasn't funded. So I used words like ionic conductivity and solid state electrolyte and so forth and so on, fundamental material science and so forth, the study of how ions conduct in materials. So it is true that in that time period, the funding of batteries has also increased. So I think it's probably, a perfect storm, you might say, of all those aspects. But I don't discount the importance of the NASA funding because it really was our first big grant.
Great, thank you for answering that. And a bit of a follow-up, these collaborations that you've built, looking at this long list of various awards, did any of these collaborations, and I think that the previous slide may illustrate it a little bit more, yeah, with all those icons, that was perfect. Did any of those collaborations with different agencies or groups come as a surprise to you? Like you hadn't realized that, oh, they would be interested in building a connection with us?
Well, the Jet Propulsion Laboratory has been a wonderful collaborator. William West at JPL and James Wu at Glenn Research. We have kind of collaborated off and on for many years. The NASA EPSCoR gave us really enough money to do that and do that well. So that wasn't a surprise. General Motors was a little bit of a surprise to me. They build internal combustion engines, but now they're going to move completely to electric vehicles. So that one was a little bit of surprise to us. And I think as a result of the NASA funding and also the DOE funding. The Department of Physics collaboration, that was ongoing. It turns out that particular faculty member, Professor Shastri, was a PhD student here at Iowa State. And that collaboration was fostered early on when he was a PhD student here. So that worked out very well and followed through. But some of them have been a little bit of surprise where, you get this random email, hey, saw this presentation, saw that you're funded by NASA. What are you doing in this area? Maybe we could work together. So some of it has been surprising, but some of it is followed, as I say, because faculty members like myself, we're kind of constantly working on opportunities for my students. And that's been one of the downsides of COVID. The NASA laboratories have been shut down even more than Iowa State, and we have not been able to send our students to work at the JPL laboratories or the Glenn Research Center. In the past, I've had summer internships and so forth, and we're looking forward to that with things improving, to sending students to work at JPL and Glenn Research Center.
Great, thank you.
You're welcome.
And it looked like we may have, I wasn't sure if another audience member had a question, so I just want to give a little bit of a time.
Sure.
Can I jump in real quick?
Yeah, please, Eric.
Yeah. Hey, Steve. I'm an IPA rotator here in EPSCoR, and actually I'm a social scientist. I'm at Boise State University, and I'm
Wonderful. Still
here because I onboarded during the pandemic, and I was really curious. I've got a fairly decent, so I'm gonna ask a question as a PI, because I have a fairly good relationship with the Idaho EPSCoR folks in general. However, I'm curious if the Iowa EPSCoR program are seeing proposals, applications, interests from social scientists. It's been kind of a hard nut for me to crack. I've cracked it in a small way, but then I came here to NSF and I can't follow up until I go back. But I'm kind of curious. I've asked this of other EPSCoR NASA folks too. Are you starting to see that disciplinary diversity that NSF is promoting these days?
Yeah, that's a real good question, Eric, and I don't have an answer for you. If I had to say, in Iowa, our types of proposals through the Iowa EPSCoR effort have been, I'll use the word technology, more physical research and technologically related. The programs have been run through material science. I've had 2, aerospace engineering and others. That doesn't mean there aren't, because there are real critical issues, as you know better than I, about long duration space flights and so forth and so on. So I think that's a really important aspect, and I'm sure there are activities, but none that I'm aware of, though. And I could do a quick query to our Iowa Space Grants Consortium director, and then ask them what their experience is in that. The way we run we have kind of 2 tracks to our Iowa EPSCoR. This one that I'm running is kind of the biggest one. It's the big $750 million research program. But then parallel to that, we have the Iowa Space Grant Consortium. And this is a consortium of 4 universities: Iowa State, University of Iowa, University of Northern Iowa, and then Drake University. And they do a lot of different things. They have student programs, high school student programs, and lots of different things that probably things like social sciences would fall into. And so I'm sure there's something there. But the bigger grants like I'm talking about here seem to be always in the physical sciences and engineering research areas.
Yeah, I mean, I'm not surprised. I mean, that's pretty much describes the Idaho NASA connection as well. In fact, my first small proposal to them, they were like, "Well, nobody's ever proposed something like this before. It's always been on the tech side."
Yeah.
But, going through the NASA Roses solicitation, I mean, over the last 5 years, they've really increased the opportunities for social science. So which is awesome, but we just don't know. We don't know about those kind of things, so we're missing out on those relationship building things that you just described.
So what I would recommend you do, and this is what I've done. See, I jumped kind of over or around or whatever the Iowa Space Consortium group and went directly to my colleagues at NASA.
Yeah.
So I knew of James Wu and Will West really before I started some of this activity. So, and then what happens is then you get that connection. And then when I wrote it was a pre-proposal competition for these big grants, and you have to win because Iowa's small enough. You only get 1 proposal to submit.
Right.
And so you had to win internally. Well, because I had developed these strong collaborations with JPL and even Huntsville and Marshall and Glenn, it really helped strengthen my proposal activity. So in your case, you presumably, or I would expect you to have collaborators at NASA working in these very critical areas, and you build those collaborations up. Maybe if you can, exchange a student by hook or by crook, or invite them to Idaho, and build that collaboration so that when you write that proposal, then you can say, look, we've already collaborated. We've already done these things. In my case, we'd already published 2 or 3 papers. And so it kind of lifts you up, as it were, a bit in the competitive level when you've already got established collaborations.
Yeah, and that's exactly where I was in this trajectory when I accepted the IPA position.
Oh,
so
yeah.
I need to jump to another meeting, but I really appreciate hearing about your projects, and
Well, thanks, Eric.
Thanks for everybody else that showed up, and thanks, Kevin. Good to see you here.
Yeah, thanks, everyone.
Yeah, thank you very much for taking the time to join us today. And we still have a few PIs here in a few minutes. So actually, if you had the time, one very quick follow-up question is,
Yeah.
I noticed that there is this tremendous expansion in awards from the original award. Part of that also means that there's an expansion in award administration and all of the paperwork required to keep up with everything. Is there anything that you wish that you knew at the beginning of this whole story that would have made your life easier in keeping everything on track?
Not so much what I knew, but Iowa State was slow to catch up to that. So in my first grant, we just didn't have the financial systems in place to help PIs manage these large grants and manage all of these grants. We were in put into a position with our state government that they said, you're not going to get any more money unless you get your financial house in order. There was no malfeasance or anything. We just didn't have the proper grant management and all kinds of fiscal things that were just out of date, and old operating systems and so forth. We were still using mainframe computers and all of that to maintain financial records. So in that time frame, 2017, 18 or so, we went to a web-based system called Workday. And at the same time that we all went to Workday, we developed 2 new programs, 2 new groups at Iowa State, one called Finance Delivery and one called Improved Service. And improved service has a lot to do with facilities, planning and management, all that. But the finance delivery, they made a concerted effort to totally reorganize how they did all of the financial management, including research and contracts and grants. It was kind of a hard pill to swallow, because we faculty were used to having a grant administrator right in our department, and he or she managed our grants, did it all manually, did it with a pencil and paper, but they were there locally. They took all those people out of the department and grouped them in groups. College of Engineering group, Liberal Arts and Sciences group, and then added more people to that group. And by doing so, everything switched to email. I don't see these people. It's all by email, but they're there running in the background now, managing all of this paperwork. And in doing 2 things, going to a uniform system called Workday and adding more people, and taking the people out of the department, because if you put a person in a department, if that person's not busy, what do? Well, they put them in pods, and 2 or 3 people are managing 4 or 5 departments. Someone's available all the time, and as a result of that, we get better service. So the thing that I would say about that question is, I wish Iowa State had been better prepared when I first got started. They solved the problem, and now it's very good. But it did, you're absolutely right. It took horsepower and commitment to totally redo our finance system and redo the way in which we managed our finances. And so in the end, it's worked out really, really well.
Great, thank you very much. And I think that I filled the last minutes of our question time with that one.
Very good. Thanks, Kevin. Appreciate it.
All right, thanks again. And it was wonderful having you here.
Oh, you're welcome. Thanks so much, and appreciate the invitation to talk about our NASA EPSCoR work. We're really, really proud of it, and we're really grateful for the support that NASA EPSCoR program has given us.
Great, thank you. Have a wonderful day.
Yeah, thanks. Appreciate it. Bye.